Welcome to Maths with EJD. I'm still talking about tests for convergence. Previously, we had considered the nth term test for divergence, and we also considered the integral test. Okay, let me just refer to this right now again. Talking about tests for convergence. Okay, we have the nth term test for divergence. That was already taken care of. Then we have taken care of the integral test. Integral test done. Then this video is going to focus on comparison test. Comparison test. So this is done. So this is going to be done now. And then after comparison test, there'll be ratio test. Okay. So the next video after this will be on ratio test. So let's move into this right now. All right, let's talk about comparison test. Comparison test for convergence, that is. So the idea here, the concept of comparison test is such that if you compare, if you compare a sequence AN with another sequence BN, okay, based on that comparison, if 0 is less than or equal to AN is less than or equal to BN. That is, AN lies between 0 and BN. Okay. AN lies between 0 and BN for all N. For all N. And the series BN converges. Okay. The series BN converges. Then the series AN also converges. So look at all those conditions. Given the sequences AN and BN, if sequence AN lies between 0 and BN for all N, and the sequence BN converges, that automatically means that AN that is between 0 and BN also converges. That is one aspect of that. The other condition is this, that if, okay, I guess I want to change now. If AN is greater than or equal to Bn is greater than or equal to 0. Okay. And okay, let me just follow the same thing. Uh if An is greater than or equal to Bn, which is greater than or equal to 0, and the series Bn diverges, diverges, then then okay, let me take it down still. Then it simply means that the series AN also diverges. So those are the two conditions for comparison test. So we have this first part, that if we compare AN and BN, and AN lies between 0 and BN for all N, and if the series BN converges, then the series AN also converges. So we also have the other part, which says that if AN is bigger than BN, the sequence BAN is greater than the sequence BN, and BN itself is greater than 0. So, I mean, it's as good as saying that 0 is less than or equal to BN is less than or equal to AN. All right. That is, BN is now between AN and 0. So, and if BN diverges in that situation, that means that AN also diverges. That's the basic concept there. So let's move on and do some examples. So let's take the first example. So example 1. Okay. Um, we want to test summation n equals 1 to infinity, the series 1 over n cube plus 1. So we want to test this. Okay. So we can compare, we can compare the series n equals 1 to infinity all over 1, I mean 1 over n cube, which is a p series. It's a p series. I think the concept of p series. Okay, we are going to see that for series that diverge. So never mind. I'm going to talk about it when we get to after all this test on convergence. The next video is going to be on divergence of certain series. So P series is one of such series. So compare this summation of 1 over n cube, for a P series with P, which is equal to 3, and of course 3 is greater than 1, of course. So compare this now, okay, um, with okay, this is what we want to compare. So, this is what we have, 1 over n cube plus 1. All right. So if we take out the 1, I will just have this normal P series now. So if you compare that, you'll see that 1 over n cube plus 1 is less than or equal to 1 over n cube for all n greater than or equal to 1. What that simply means is that, if you, for any value of n, for instance, if n is 0, right? If n is 0, this is 1, and this one will be undefined. 0 is way less than infinity. So if n is 1, for instance, this will be half, and this will be 1, all right? So this is always less than or equal to this. Where are they even equal? At what point are they going to be equal even? Maybe at some fractional value, right? Yeah. So you consider 1 over n cube plus 1 is always less than 1 over n cube. You can just test that by putting, okay, with 0 even, it's clear. With 0, the left-hand side is 1, and the right-hand side is undefined. So 1 is way less than undefined, infinity. And next, if you try 1, so you have 1 over 2 on the other side, on the left-hand side, and on the right-hand side, you have 1 over 1, which is 1. So half is less than 1. So that is true for all n greater than or equal to 1. So that's the comparison we have done right there. And in this case now if you look at, you see that if you do the limit as n tends to infinity of 1 over n cube, okay, that means that you have, so I mean, the first thing you should do is substitute directly. That's 1 over infinity cube. That's 1 over infinity. And that is simply 0. And 0 is a good answer, right? 0 means the limit converges to 0. So based on that now, so we can see that the function we are comparing the original function with actually converges. So based on that, we can make a conclusion that uh, since so since the series 1 over n cube converges, since it converges, then we can also say that the original series you have 1 over n cube plus 1 also converges. It also converges. And that's what we have. Okay, let me try to make it bolder. So since since the series 1 over n cube converges, then of course this series 1 over n cube plus 1 also converges. And the rule that is based on is the fact that the original function is actually less than than the function we are comparing it with, which actually converges. So it means that so we can as well say this is 0 less than or equal to, so this is like 0 less than or equal to bn less than or equal to an. Okay, that's going by this first situation now. Okay, uh or better still, I think it works better for the other side of things. I think it's the second one, right? Where you have the given function. The given function is 1 over n cubed, and that is actually so an is greater than bn. So here now we see that the function we're given, so this is more like, let's say this is our an, this is bn. So an now is greater than bn. Oh, okay. What's this now? So this is less. Okay. 0 is less than or equal to n is less than or equal to bn. Yeah, I think it's the less than part of things now. So this is bn. This is like an. We can take it like this. And of course, 0 is less than this because, I mean, if you put it at 0, you are going to get 1. So you still have 0 less than or equal to this. So in that case now, and since the bn converges, then an automatically converges. So that's the kind of idea we have for that. Okay, that's the comparison test. The comparison test goes there. So let's take one more example. That interesting example, 1 over n is always surfacing. Let's do that. So example 2 now. Example 2. So we want to test summation from n equals 1 to infinity of 1 over n. So let's test this and see what happens. So first of all, what is the closest thing we can compare this with? So let's try to compare with summation n equals 1 to infinity. So we can compare that it's 1 over 2n. We can compare it to that series 1 over 2n. So I mean, this is more like multiplying the original thing we had by half. So this is actually, so we say this scales, right? It actually scales. So this scales, but diverges. So it also diverges. Normally 1 over n diverges. So this scales but diverges, um like, so we know from everything we've done so far, we know that but diverges like summation. I mean the series 1 over n, like that. So in this case, um so we have that diverging. We have it diverging. Trying to see, divide by n, 1 over n over 2, 0, 2 down there. Okay, so to compare with that, it's all that, so that actually gets to diverge. In the original situation, I'm trying to remember what we did there. So if you do this, if you put infinity, 1 over infinity is 0. Okay, yeah. So when we say, so in the first test, if we have 0, right, the test is inconclusive. Yeah, I remember that. Okay, yeah. So, but I mean, this other one gives a very good example for us. Let me see if I can get another example for comparison test. Okay, another example for comparison test. So let's see if we can make it up to 3 examples. Okay, so imagine this now. Let's see this case. Let me do example 3. Example 3 now. So tests, like we always say, tests the series n equals 1 to infinity of 2 over n squared plus 1. So normally, uh, so we need to choose something to compare it with. So let's say we need to compare 2 over n squared plus 1 with 1 over n squared. Okay. So, and of course, as you're going to see later, this is actually a P series too. This is a P series. Any series that has a power on top of it like this, a P series, and it's with P equals 2. And since 2 is greater than 1, right? Uh, this is, and it is known to converge, which is known to converge. Okay, it's known to converge. So in that case, we can now check the inequality. So we say for n greater than or equal to 1, just like I did without writing it down the other time. For n is greater than or equal to 1. So you can see that for n greater than or equal to 1, so if you put, let's say if you put 1, okay, let's even put 0. If you put 0, this will be 2. If you put 0 here, this will be undefined. So then if you put 1 also, this is 2 over 2, that'll be 1. And if you put 1 here, that'll be 1 also. So they are like equal. So in that case, we can say that 2 over n squared plus 1 is less than or equal to 2 over n squared. So the original thing we're given is this one. So this is more like your an, and this is more like your bn. So we can say this is actually less than or equal to 0 because you can see it hasn't gone to 0 all that while. And so uh this is also true because, I mean, this expression is true because okay, I guess I want to color code now. This is true. Thought I changed it. This is true because n squared plus 1 is greater than n squared. If you divide by something bigger, the answer is smaller. So that's why this is smaller than this. Okay, so that's there. All right. So if we apply the comparison test now, so we can see that since the series n equals 1 to infinity of 2 over n squared is a multiple, it's a multiple of a convergent, it's a multiple of a convergent P series, which we're going to see very soon, then we can say that the series n equals summation of n equals 1 for n equals 1 to infinity of 2 over n squared plus 1 also converges. It also converges by the comparison test. It also converges by the comparison test. Okay, so that's how that is going to be. So that brings us to the end of the comparison test. So watch out for the ratio test. So if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And of course, comment, let me know how helpful these videos are for you. And of course, let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. And don't forget to like and share so that more people can have access to this great content. Till I come your way again, have a nice time. Bye.